Welcome to Study Loop.
So here we are given the helium gas, which is going through different thermodynamic changes. So first we'll have the transition from the point 1 of or the first state, and I'll mark the state on the PV diagram, for example, right here. And from this state, point 1, the helium gas will go down in pressure but expand in volume simultaneously, meaning that this is happening under a constant temperature. So, for example, here will be the second state, and here is the process happening under constant temperature. Next, from the point 2, under constant pressure, the volume will be compressed. So the pressure will be constant, but the volume will compress, like this, to this point, to the initial volume. So here is the initial volume, final volume, and also different pressures. This is P1, this is P2, for the sake of the PV diagram. So we also know that at the point 3, nearby this V1, there will be V3. They're very close to each other on a PV diagram. So I'll just say immediately that V1 equals V3, which is equal to 1.5 liters as given in the problem. And that from point 1 to point 2, the temperature T1 will equal the temperature T2. This is process going on under a constant temperature, which is 300 kelvins. So this was important for the part A of the problem. Now in the part B of the problem, we actually need to evaluate 3 different things. We need to find the volume V2 at the point 2, we need to find the pressure at the point 3, or the state 3, and we need to find the temperature at the state 3. So since between points 1 and 2, the process is going under a constant temperature, we can use this relation, P1 V1 equals P2 V2. And from here, we can derive this term, right, the V2 term. So because the temperature is constant in this process. So V2 equals P1 over P2 times V1. We can then substitute and say this is 1 times 10 to the 5th power. These are pascals. This is going to be multiplied with 1.5 liters. And this is going to be over 2.5 10 to the 5th power. This is multiplied. This is the multiplying point here. And this equals, so from here, when we put these values into a calculator, we obtain that 2 equals 6 liters. Now, for the pressure on the third state, we know that the process is isobaric process, so it's going under a constant pressure, and we can then state this statement right here. P2 equals P3. Very important, because this allows us to use the given value for the P2 to express the pressure at the point 3. So this is going to imply that P3 equals 2.5 times 10 to the 4th power pascals. And also one thing here is this is not on the 5th power but on the 4th power. This was a typo. But in the calculator you put these values with the 4th power. So, and this is going to be in pascals. So the last thing we need to evaluate here is, for the part B, is the temperature, so T3. And since we know that the process from state 2 to state 3 is going under a constant pressure, we can then use this formula. Since pressure is constant, then the volumes and the temperatures are in this relationship. And from this relationship, we can say that T3 equals T2 times V2 over V3, which when we substitute the values is 1.5 over 6. So you can see now why we first evaluated the volume V3, because without the volume V3 we couldn't evaluate the temperature T3. So this times 300 kelvins, and then we obtain finally that T3 equals 75 kelvins. This is for the part B. Now for the part C of this problem is the question of work. So the total work is the work from the point 1 to the point 2 plus the work from the point 2 to the point 3. For the work from the point 1 to the point 2, we know that the temperature is constant, so both pressure and volume are changing. Therefore, pressure is a function of volume, and we need to use the formula for the work that is a result of the integration with the natural logarithm. So this work will be equal to nRT natural logarithm over of V2 over V1. From the ideal gas formula, we can substitute for this part and say that this equals P1 V1 times natural logarithm of V2 over V1. So again, I repeat, this is the result from the integration form, when we integrate pressure as a function of volume, which is derived from the ideal gas equation. We can relate P to V in a functional form from that equation. So here we can simply substitute the known values. Work from 1 to 2 is, I'll use angular brackets, square brackets, 1.10 to the 5th power pascals times 1.5 times 10 to the minus 3rd power. This is for the volume, V1. And then in the natural logarithm, we have 6 over 1.5. And this will be in joules. When we place these values into a calculator and evaluate, we obtain that the work from 1 to 2 is 208 joules. Now for the second work, for the work from the point 2 to the point 3, this is the work being done under a constant pressure. Therefore, work from 2 to 3 is equal to the pressure, the constant pressure P2 times the change in volume. This is the important relation. So we can evaluate. V from point 2 to point 3 equals V2 times V3 minus V2, and then substitute the known values to find that this is equal to 2.5 times 10 to the 4th power pascals, and in brackets we have 1.5 minus 6 times 10 to the minus 3rd. This is meters cubed, and when we evaluate this, we obtain that the work done is from the point 2 to the point 3 is equal to minus 113 joules. Now, we can then say that the total work done, so the work total is 208 joules minus 113 joules, which equals to 95 joules. And for the part D, which is the last part of the problem, we have to understand that to return this gas into its original pressure and temperature, we need to stop any work that is being done. So in order to get the work being done on the gas reduced to zero, we need to stop all of the heat, or heat the gas at a constant volume. So of course, since we need to add heat to the gas, we will simply heat the gas, but we will keep the volume constant. So the heat at volume equals constant. And this is the answer for the part D. So we have solved the problem. I hope you find this helpful, and I hope to see you in another lesson. Bye.